Hello. Yeah, in this video, I will show you how to perform basic time series analysis using R. Okay, so you need to install these packages, forecast, TS series, and TTR. And let's set a random C, create a synthetic time series with 10 years and frequency 12, so monthly, and the number of data points is the number of years times frequency. Let's create a time index, and let's put components, trend plus seasonality plus noise. So it is a linear upward trend, 0.5 times time index, and get a seasonal pattern repeat, length out equal to endpoints. So it's a yearly pattern, and random noise, just the normal distribution, and then put everything together, we got our time series, simulated time series. Now we turn numeric vector into a time series object using the R function called TS. Okay, so you say TS of Y start equal to C2015-1, frequency equal to 4. Okay, so now we have turned this numerical vector into a time series object. Then we can use all the time series packages. First, let's do basic inspection and plot. We can simply just plot out all the values of the time series, and we can do summary, get the basic statistics of the values. And then, of course, we have to plot time series, just using plot my PS, gets the title, and X lab, and label, and white label. It look like that on the right. And the second basic analysis of time series is decomposition. Basically decomposed into trend, seasonal, and randomness. Okay. So one thing, we have a classic additive decomposition. We can use the function decompose of my TS object, and we can say type equal to additive. So, and then we can plot them out. You can see you have the observed, the first plot, and you have the trend. That's the extracted trend from the time series going up. And you have the seasonal, it look like periodical, right? And the random is look like the noise. And if you really want to see the values, then you can access them through the TS underscore decompose at trend and seasonal and random. Okay, and R has a function for the checks, the stationary checks. So whether the time series is stationary or time, first we can just plot out the original time series, and then we also can plot out the first difference of series. So the first difference is the current value minus the previous time point value. So what you can see is you look for whether there's a trend in the means, look like a little bit going up, or change in the variance, the variability, whether it's increase over time, decrease over time, and that's the range, the vertical range of that value. Okay. And also seasonality, if you can see something repeat over time. And then look at the first difference series. If it successfully removed all the trends and seasonality, then the first difference series would look like a random noise. Okay, so it's basically jumping around zero and not much change in variability. Okay. Of course, visualization may not be accurate. We can also do a hypothesis test called the Dickey-Fuller test for stationarity. Okay, so you can use the ADF.test. Just put my TS object in there, and also you can put the differences in there. Then you can print it out, and you can see for the original, you got a p-value 0.01, so it's a very small. Tells a lag order equal to 4. Basically, this tells you reject the null hypothesis, which is the unit root exists. So that means non-stationary. So we reject the non-stationary null hypothesis, and so we can conclude the original time series is stationary. And it may be contradictory to the graph of the raw time series. We see some linear trend going up, but that is like a deterministic trend. So here, the hypothesis test here is for testing whether you are, say, have a stochastic trend, like a random walk going up. Okay, so that is the test is for. Okay, and also from the same test on the differences, the p-value is small, also it's stationary. Okay. And we can check autocorrelation, a partial autocorrelation. Just look at the values of the data points close to each other over time. Before we do that, we can remove the trend first. So we can say we extract the residuals by fitting the linear regression model of the data point against the time. And then all the residuals, and we plot the residuals, it looks like that. So this is the detrended time points. And then we can now check the ACF and the partial ACF. And they look like that. Okay. So how do you look this to determine the P and the Q in the ARIMA model? So basically, ACF is determining the P, the autoregressive order, and count spikes outside the blue lines, and ACF determines the Q, the moving average order. Okay, so if you look at these two plots, look at it. The first, the ACF, there's 4 spikes across that blue line. Also, there's 4 on the other side, across the broad line. So we can say the P equal to, the Q equal to 4. And then for the partial ACF, you can see each side is as 2. So P equal to 2. So based on this observation, so we can actually fit a ARIMA model, so auto-regressive integrated moving average model for forecasting. The function is ARIMA of TS, and we can say order equal to C, P equal to 2, and Q equal to 4. Okay. And we can print out the summary. You can see the AR1, AR2 moving averages and the intercept, and give you the likelihood and the AIC values and all the prediction accuracy measures. Okay. And we can check the ACF for the residuals. It should look like white noise, but it seems like there's still some spikes over there. So the model fit may not be very good. We can actually try some alternatives because we think maybe it's overfitting. So we can say fit 2 ARIMA my time series order to C22, okay, fewer parameters. And we can print out the AIC. The smaller AIC should be the better. So the fit 2 actually has a smaller AIC. So maybe we should use that one, okay. And it's very interesting that R actually give you auto.arima function. It will actually let the algorithm choose the best P and Q. So you don't have to based on your plots. Okay, so the auto.arima is this function and my ts and d equal to 0, and this would give you automatically say you should fit a ARIMA 3 0 with non-zero means. Okay, and it also give you the AIC value, which and so this is what the automatic algorithm give you. Okay, and once you have the time series, you can also do smoothing. So first it's like simple moving average SMA, and then you can plot it out. It looks like that. So original, and then the simple smoothing average. And based on that, you can actually do forecasting. So you can actually do the Holt-Winters, Holt-Winters prediction. Oh, sorry, you do the exponential smoothing, and then you do the forecast based on that, h equal to 24 for 2 years, and then you can actually print them out. So you can see it's there's like a shaded area. Those are the actual predictions, the forecasts. Okay. And also you can do the ARIMA-based forecast, doing an auto-ARIMA, and then doing the forecast for 24 months, and then you can print it out to look like that. Okay. All right, so in this video we covered some basic time series analysis in R as introduction to time series in R. Thank you.